initial state and the goal state, the solution. And that would be an effective way to problem solve. This problem is well-defined. It's got a good, well-defined goal state. It's got well-defined operators. With a well-defined problem, you could do an algorithm like this. It would guarantee success. However, when we left off, I was saying, is that what you would do? The consensus answer seems to be no. And in fact, although you could program a computer to do this, we probably don't have the cognitive resources to really plan out everything, all the entire problem. And instead, what we do is often apply heuristics rather than algorithms. And heuristics are basically shortcuts. So they don't guarantee success like an algorithm. They also don't require super well-defined problems like an algorithm. In addition, they're basically little shortcuts that usually work. Most of the time, the heuristics that we use will generate the correct response. And that's probably why we use them. Probably adaptive to use them. Particularly because they consume far fewer cognitive resources. So they place far fewer demands on our resources than, say, an algorithm. And in the problem-solving literature, I'm going to give you just a couple heuristics, which are kind of heuristic strategies for problem solving. But when we get into the last thing in the course, which is decision-making, I'll come back to heuristics, because it turns out we also tend to have heuristics that we use when we're making decisions as well, which have the same characteristics. They're basically shortcuts that lower processing demands, but risk potential impairment. So, as a problem-solving heuristic, a simple problem-solving heuristic is something called hill climbing, which is also sometimes called difference reduction. And the basic idea there is every step you take, every move you make, Stalker album, but every step you take, everything you do, you go towards your goal. Just keep moving directly towards your goal. And if you do that, you may one day end up at your goal. But it actually depends on the problem, which I'll get to in a second. But it's a simple, really cognitively simple task. It doesn't have very many demands. I just move towards my goal. There's no need to think through sub-goals, which I'll get to in a minute. There's no need to map out all the problem space. It's just every step I take, I move towards my goal. And it will work if you're doing something like climbing a hill, which is why it's called hill climbing. Which is, if every step you take is upward on this hill, eventually you will make it to the top of the hill. You just have the simple heuristic, I'm going to step upward. On a hill, you will make it to the top of the hill. But, as a heuristic, again, they're not always compatible. The method of means reduction or hill climbing doesn't work in some cases. So one of the problems with a hill climbing approach is that sometimes you'll wind up at either a plateau or a local maximum. It's not the solution to the problem. So for instance, if rather than climbing a hill, you're thinking about climbing a mountain, you might have a situation where you have a local maximum, where you go up a ridge. And then you gotta go back down into the next valley before you go up the next part of the mountain. And if your heuristic, if your problem-solving heuristic was always step up, you will get just to the local maximum. So, and then you're stuck because your strategy no longer affords you a direction to go. You're So instead, another heuristic people use for particularly for more complex problems is something called a means-ends analysis. And essentially, what you're doing in that case is you're still trying to eliminate the difference between your current state and your goal state. But you identify sub-goals along the way. And particularly for hard and complex problems, identifying, well, before I get where I really want to go, I have to get to this intermediate point, is developing a sub. And then you just work towards that sub goal. And what that does is it allows you to basically break a complex problem into a number of smaller problems, into a number of smaller sub-goals. And so you can kind of focus your resources, cognitive and otherwise, on just that proximal goal, that sub-goal, the nearest sub-goal, without worrying about the whole big picture. And then when you achieve that sub-goal, you start planning and strategizing how to get to the next sub-goal. Eventually, the final sub-goal is the ultimate goal. So, like in the real world, if you're like, okay, my goal is to become like a tenured professor at a research. There were a lot of steps in it. So, I made some goals, right? Like, I gotta go to college. Do well. So I did. Right? But that was my first sub goal. And then I could focus just on doing that. And it's like, oh, I should get research experience. I did. That was another sub goal. Oh, I gotta go get a PhD. I did. That was a long sub goal. Pacing myself. Then, you know, I have to get experience that will allow me to get the job, so I got a different job. And then, so, but breaking down long, complex problems into sub-goals. And it'll work for problems that hill climbing. So if your sub-goal, your first sub-goal is to go to the red star, you know, you get there, and then you have to create a second sub-goal, say go to the green star, which may involve moving away from that ultimate goal. But your third sub-goal is your ultimate goal, and you make it. So it turns out there are a lot of problems out there where a means-ends analysis is better as a problem-solving heuristic than something like hill climbing, because there are points at which you have to move away from your ultimate goal to eventually get there. And one classic, and yes, completely politically incorrect, really classic problem that has been used in this problem-solving research area is a problem called emissions and cannibals. And the basic problem setup is the following. There are, say, 3, although you can make it as many as you want, which just makes the task more steps. But the simplest version is there are 3 missionaries and 3 cannibals on one side of the river, and they need to get to the other side. The boat can only carry 2 people at a time. There can never be more cannibals than missions in one location, or the cannibals will eat the missions. How do you cross it? And this mission and cannibals problem has been used a bunch in labs to look, rather than at kind of insight, aha problem solving, at one of these more kind of iterative types of problems. If you actually Google missions and cannibals, there are all sorts of places online where you can actually play and try to figure out your solution. And it really is a classic example that's been used in the problem-solving literature. And it is an example that suggests that people would need to use something like a means-ends analysis rather than a hill climbing strategy you've got two cannibals across the river, but to actually accomplish the problem, to solve the problem, you actually have to take them back and start taking cannibals that were across the river back to the original side and leaving them there. Which is that kind of moving away from your eventual goal. Slow and painful online video game. But, in fact, at some point you have to have all three of them. At least one of the solutions is to have all three of them. Even though you have two of them across, get them all back to the other side, and then eventually move them across. And you can make this problem actually really hard to solve by just increasing the number of missions and cannibals. So some of the evidence we have that people actually use sub-goals comes from some work using this mission and cannibal problem, in which what they did was they gave people, actually in this particular case, they gave people a version of the problem with 5 missions and 5 missionaries and 5 cannibals, which is a pretty long problem to solve. And there are a bunch of cases where you have people cross the river and have to start taking them back the other way in order to solve the problem. And in this experiment, what they did was half the subjects received a sub-goal hint, a place along the way that is part of an efficient solution. The other half received no sub-goal hint. And the 5 that received the sub-goal hint was that at some point during this solution, you want to have 3 cannibals across the river without the boat. And if you gave people that sub-goal and allowed them to focus their resources on getting to that point, and then once they got there, there was less to do to get to the final point. It had a big benefit. So in the no-hint group, it took them on average 30 moves to solve this problem. But with the hint, that was reduced to 20. So basically cutting in third the number of moves you needed to make if you allowed people, or if you gave people the something. The bottom line there is that it suggests that people do occasionally, and certainly should or can, effectively use sub-goals. And if you can identify a good sub-goal, it allows you to simplify problems, working just towards